Today we're going to take a look at section 4.4, which is the Fundamental Theorem of Calculus. Always like to tell students anytime you see the fundamental theorem, you know it's really important, right? Really, really important. I haven't looked at the review guide, but I'm going to guess that this is one of those ones where I'm going to tell you, you need to memorize it so you can write it down for me on the test. It's that important. So let me talk to you first about what the Fundamental Theorem of Calculus is. We have done all the parts of this theorem, we just haven't put it together yet. So here's what it says. If f is continuous on an interval ab, and capital F is the antiderivative of f, then the definite integral from a to b of f of x dx, which we have approximated in many ways, right? We've approximated it with rectangles, we've used some geometric formulas, we've talked about how we can separate things and whatever when we know certain pieces, but we can actually find it directly by taking the antiderivative and evaluating at the upper limit b, the lower limit a, and subtracting those values. So obviously we have to do some, right? So let's take a look. All right, so you're about to take a gateway quiz for me about antiderivatives, so I hope you're brushed up and really good on some of these antiderivatives. What is the antiderivative of negative 3x? All right, negative 3 over 2x squared, or you could do negative 3x squared over 2, however you think about that. How about the plus 4? 4x. And I'm going to, the plus c, I'm going to put it in here for this one so you can see what's about to happen. Remember, when we do your quiz today, they're going to all have plus c's on them, right? So if you need to write that at the top of your quiz when you first get it down or whatever. I had a student forget it, again, in my quiz last week on every single problem. He forgot it. He wouldn't have gotten his full extra credit. However, he did miss all of them because of that. So don't do that. What you're going to do next is you're going to put a line at the back, just a vertical line. You're going to put your limits of integration on the top and the bottom of that line. So there's a 5 here and there's a 2 here. And then you're going to actually evaluate that. So you're going to plug in the 5. So you're going to do negative 3 halves times 5 squared plus 4 times 5. And right now I'm going to write down plus c, but you're going to see very quickly that I don't need it. And then you're going to subtract, and you're going to plug in the same thing with the 2. So negative 3 halves, 2 squared, plus 4 times 2, plus c. So can somebody tell me what's going to happen with my plus c's? Yeah, they're going to cancel out. They're going to add to 0, right? So when we're working with definite integrals like this, you don't have to put the plus c because it will cancel itself out, okay? So if you leave them off for these, which is what most people do, that's totally fine. This is not necessary. The rest of it, you're welcome to grab a calculator and find an approximation for. As long as you're plugging things into what's going to end up being decimals or fractions or whatever, your calculator is very good at that. If you're plugging it into radical, please don't approximate. That's not a good plan. We want to leave it exact. But this one doesn't have any radicals. So if you evaluate this with your calculator, you can use a decimal or a fraction to get this one. And if you want, you can do each parenthesis separate and then subtract if you feel like it would be working like that way better. If you want, you can plug this into y1 and use a table. You could do it that way. And I want to show you one cool trick, but not on this problem just yet, for evaluating. So what did we get for our value for our definite integral? Anybody have it yet? Do you have it, Mateo? No? I see a lot of you with calculators from just looking around at other people like, they're going to do it, I don't have to.
It's negative 19.5.
That's what I have as well, Emma. Thank you. Good. Speak up, speak up. Negative 19.5. Okay, yeah, that's correct. So I want you to try something real quick. We've got this solution. It is the correct answer, but I want to show you something really cool that your calculator will do. All right, so I want you to hit y equals. If you have a TI Inspire, I don't know how it works in your TI Inspire. I apologize about that. But if you've got a TI 89, or sorry, TI 84, 83, those kind of versions, if you put the original equation, negative 3x plus 4, into y1. Okay? Everybody good with that so far? All right, so I want you to go out to the regular screen, like where you just did all that adding and subtracting probably. And I want you to choose Math 9. Now, depending on your Math 9, it will do one of two things. It will either, if you have one of the newer operating systems, which I don't, it will either give you, if this is the newer one, something that looks like this. Okay, how many of your calculators look like that when you selected Math 9? Okay, a handful of you. The other thing it might give you is something that looks like this. So who has this on your calculator? Okay, so I think that there's a whole bunch of you who did not raise your hand. So do you guys, all who didn't raise your hand, not have a version like this? Different calculator? Okay, the first one, what you do is you enter exactly what you have in your question. So I would put y1 since we put it in y1. I would put an x right here because x is your variable. You would put your lower limit right here, that's 2, and your upper limit, you can't hardly see that, my pen's too thick. A 2 here. Is that any better? Two?
Are you putting this in the right screen?
No, you're in the regular screen of your calculator. You should be in the regular calculator screen. So I'm going to erase, oops, I said erase. Let's try that. So you're going to put the 2 down here, you're going to put the 5 up here. Okay? Hit enter, it's going to give you negative 19.5. Cool stuff. If you have the other version, if yours looks like what mine would look like if I were doing this problem, you have to do a little bit more of language that looks like programming. So you have to tell it that your function's y1. You put a comma and you tell it your variable's x. Put another comma and you tell it your lower limit of integration is 2. Another comma and your upper limit of integration is 5. You close the parenthesis, or don't, it doesn't really matter on the closing, but you hit enter and it will give you 19.5 as well, negative 19.5. Okay, do you want to see one more cool thing? All right, go back to your calculator. You should have y equals still in there, right? All that's really good. I want you to make your calculator screen, I'll do this one with you. It needs to include the limits of integration from 2 to 5. So just do it in a regular standard screen, I think will work on this. So we had negative 3x plus 4. And just do zoom 6. Okay, everybody good? Looks like a line. It's a decreasing line, right? Everybody good? All right, I want you to hit second trace, which is the calc menu. And I look at option number 7. What does option number 7 say?
Integral of fx.
Yeah, do you guys see that? Okay, that looks like the notation we're using. That's the one we're going to pick. So select number 7. And at the bottom of your calculator screen, I wish you could display it. I'm sorry, I can't. It actually says lower limit. Do you guys see that? Type 2. And when it hit enter. And then when it says upper limit, you will think you will type 5 and press enter. That's why I have to show you that, is because of that reaction. Thank you so much, Emma.
Sorry.
That was what I was shooting for. No, it always happens because it's exciting. You saw something happen in your graph, right? Do you also see why you ended up with a negative? It's because it's underneath the graph, right? All of the ones we looked at last time and that we've been looking at so far in this chapter have been graphs that have been above the axis. So all of our area has been what we would call a positive area. And while we all recognize, of course, that area is neither a positive nor negative quantity, it's just, it's space that we're talking about, right? So you could say it's positive quantity, negative doesn't make any sense. In this context, negative simply means that it's beneath the x-axis. It tells you the answer at the bottom of your screen, negative 19.5. Okay, so all those cool calculator tricks are super cool calculator tricks, and they're great for verifying your answers. But honestly, they're not any better than the back of the book on the odd ones, right? If you were looking at that. Or they're not any better than, WebAssign telling you you're getting it wrong and you finally get it right. They don't actually tell you how to get there with calculus, correct? The calculator's not even using calculus. The calculator's doing this with those infinitely many rectangles with Riemann sums and limits of integration. That's what it's doing. Okay? So my point is that it won't give you this. it won't give you the antiderivative to doing that. You still have to do that by hand. However, it's a really cool check step if you're wanting to verify. So as we're working our way through, you're welcome to use any of those features. Either evaluation, just to plugging it in. You're welcome to use the function integration if you want to do it from that perspective. It doesn't matter to me which ones you use, but you still have to show your antiderivative, like we did here, and you have to show the first step where it shows the numbers plugged in. Okay? And then after that, you can simplify in whatever fashion makes sense. The one caveat, again, is that if you're dealing with radicals or sine functions or something that end up with radicals, you need to keep it in radical form. So then the calculator is, again, approximating, and that's great, but you can't use that as your final answer. All right, so we're going to try something that does, in fact, have some radicals now. Oh, and the other thing, too, about the calculator when you're looking at it graphing that way is that whatever the x values are that you're finding the limit between, ours were 2 and 5, they have to be in the window. So if you really like the one where it shaded it in for you, you have to make sure that the 2 and the 5 are actually in your window. So if your window here had gone from -10 to 0, it would give you an error, and that's why, is because it's not in the screen. All right, so let's take a look at a few more. Number 2, we want the antiderivative of 1 plus sine x. So what's the antiderivative of 1? Yep. And then the antiderivative of sine of x. Minus cosine of x. Okay, we're fine. And then we're going to draw that vertical bar at the back. We don't need the plus c. If you want to put it, it's great, but you don't really have to have it. We're going to go from 0 to pi. Okay, so everything I'm showing is exactly what you have to show. And then we're going to evaluate it. So we're going to plug in pi minus cosine of pi. And then we're going to subtract 0 minus cosine of 0. You can't put this in your calculator. You can get approximation, but pi itself is already irrational, right? So it's not going to be helpful. What about these quantities? What's the cosine of pi and what's the cosine of 0? Let's do cosine of pi first. -1. So I have the pi at the beginning already, and then I have minus -1. And then I have minus, and then there's a 0. I don't need to necessarily write that down. What's the cosine of 0? 1. So there's a negative already there, and then I have the 1 for the cosine of 0. So we're going to change some signs. That's addition now. This one's addition. So what's my solution in exact form? Yep, pi plus 2. And you're done. All right. Theorem 411 is actually called the second fundamental theorem of calculus. And it hits on the relationship between derivatives and antiderivatives. So it tells you if you have a function continuous on an interval a,b, and the antiderivative, f of x, from a to x of f of t dt, that's what it actually is, that's the antiderivative, then what this is saying is that if you take the derivative of the antiderivative, you get back the original function. And that should seem fairly straightforward. The derivative of the antiderivative is the original function. So it feels a lot like when somebody says, they'll do these tricks on email. Back in the day, my grandparents had a small business, and email was the new big thing. And so my grandparents, who were quite a bit older at that time, were not afraid of technology. They were into email, and you'd see these email chain letter things that come around, and they'd do funny things like this. They'd say, take the year, add this to it, and then multiply it by this, and then divide it by that, and then subtract this off. What do you end up with? And it would tell you the year that you end up with, and my grandfather was like, whoa, right? But all it did was just undo all the operations it had you do, right? That's all this is doing. It's undoing an operation you just did. It's an antiderivative and a derivative. You should end up with the same thing you started with. Now, there's one small difference that you might notice is that there's this funny business of of having these limits of integration, and there is some weirdness that happens. I'll show you that. But the basic idea is that when you take the derivative of the antiderivative, you get back what you started with. Now, take a look at how this problem is set up and tell me if you can see if you can tell me what makes this look a little different than the previous slide. Yeah, it's not x in the numerator or in the top upper limit of integration. It's sine of x, right? So there is going to be something a little weird that's going to happen because of the sine of x going on. Okay, so it works just fine. Limit, the derivative of antiderivative when it's a to x, and a can actually be anything, any number at the bottom, not a variable, but any number at the bottom, any variable at the top, or in the variable x at the top. But when the variable at the top is actually another function, there are some differences that happen. So what we're going to do is we're going to actually find the derivative f prime of each of these. So you have to be a little bit careful. What we'd like to say is that it's just t plus 2, right? It's the derivative of the antiderivative. The notations sort of cancel out, right? Like this notation cancels this notation out. That's what we'd really like to say happens. And it would be true if that upper limit were x, but it isn't. It's the sine of x. So let me show you how it actually gets changed. What happens is that we do have the t plus 2, which we will evaluate with x, or with sine of x here in a minute. But we also have the derivative of what's up here. What is the derivative of sine of x? Cosine of x. So I'm going to show you why that works out here in just a second, but this is the nuts and bolts of where you're headed, and this is what you would be expected to be able to do. Of course, I can't have t and x in the same problem. T is not really in my problem. It's the sine of x in my problem. So sine x plus 2 times cosine of x, and the final result, which I have yet to show you why exactly, but is sine x cosine x plus 2 cosine x. Okay, so you simply have to take the derivative of that limit of integration that's not just x. Okay, that's what you really have to do. So let me show you why it works. We're going to actually do this problem out longhand. That is, we're going to take the antiderivative, and then we're going to take the derivative, and we're going to see what happens. So what is the antiderivative from 0 to t plus 2 of the sine, I got the numbers in the wrong place, sine x up here, t plus 2 down here. So just looking at t plus 2, what's the antiderivative of t? Okay, t is my variable, so it's like x. So what would be the derivative of just, or the antiderivative of just x? Yeah, it would be like x squared over 2. So this would be t squared over 2, or you could say 1/2 t squared. Okay, t is my variable in the problem. And then what's the antiderivative of 2? 2x or 2t in this problem, right, exactly. Okay, so this is the antiderivative of the t plus 2. Okay, is everybody okay so far? Okay. And then what we're supposed to do with the fundamental theorem of calculus is we're supposed to evaluate that from 0 to sine of t, or sine of x, excuse me, my letters all mixed up. So we're going to plug them in. We're going to plug in sine of x. So I have now, I'm going to write that 1/2 in front. So I have the sine of x squared plus 2 sine of x. And I have minus 1/2 sine of 0, not sine, 1/2 0 squared plus 2 times 0. And that's what we just learned on the last couple of problems, right? We evaluated the top nut value, which happens to be a function here, sine x. We evaluated the lower value, which is 0, and we're going to simplify some things. So if we simplify some things, what happens to the 1/2 0 squared? That's 0. How about the 2 times 0? That's 0. So I actually only end up with the first piece from it there, right? I have 1/2 sine x squared plus 2 sine x. Okay, so what did I find? Well, I found capital F of x, right? That's what I actually found. All I did was simplify, if you will, the right-hand side of the equation. But what I want to find now is I want to find the derivative of this. The notation that they did, yeah. So I want to find the derivative of this. So what's the derivative of 1/2 sine of x squared? So I know we're mixing the derivatives and antiderivatives in the same problem, which makes it kind of fuzzy. But this is yeah, you're right.
Okay, pull the 2 from the top.
Okay, what rule are you using?
Product.
The product rule, not product.
Chain.
The power rule and the chain rule. Yeah, power rule and chain rule. Okay, so you want to take your 1/2 down, or the 2 down with the 1/2, and then what?
Times sine of x. And then the derivative of sine of x was just cosine of x.
Right.
Times that.
And then plus,
2 cosine of x.
so the 1/2 and the 2, those cancel. And sure enough, you're left with exactly the same thing we did the other direction, right? And the reason that's happening is because you end up with a chain rule, right? That's where that cosine came from, is because I actually had to take the derivative of the sine of x once it was evaluated in there. So that's why at the end, if you don't have simply x as your upper limit of integration, you have to do the derivative of that component as well, is because there's actually a chain rule present in your problem. Okay, so let's try another one. This one has a couple other tricks to it that the first one didn't. What do you notice is different about this problem?
They're both variables.
They're both variables. That's not okay. The original way that we set up this problem has to have a constant down there. You can't just turn it into a variable and just operate like it was a number. It's not a number, it's a variable. So here's what we do. There was a theorem that we had, I can't remember which section it was in, maybe in 4.2, that talked about if you or maybe even last time, I think it was last time, that if you went from A to B, right, with the limit of integration, like this, and the C value was between A and B, I'll write it that way, that you could break this apart. For some reason it was helpful and say, oh, we'll go from A to C, and then we'll go from C to B. Do you guys remember that property? We didn't have to use it to do anything, but we had it as a property. I drew a picture of it, and I told you if you took the graph and you just broke it down in a piece in the middle, and you did this piece, and then you added to this piece, obviously it's the same as the whole piece to begin with. Everybody remember this, okay? This is the property we're going to use. So I'm going to delete it off my screen, but this is what we're going to be doing. So we can use, try it one more time. We can use any number we want for this breaking apart number. It does not matter. So I tend to just use 0. But if you want to use 1 or whatever, it won't make any difference, because that property over here, this theorem that we had, works for any number A. So pick your favorite letter, pick your favorite number to represent that and go with it. So I'm going to use 0. And what we can do is we can actually break this apart. So we're going to break it apart in a couple of steps. I'm going to go from x to 0 of t squared plus 4 dt, and then 0 to 3 minus x of t squared plus 4 dt. Now, one piece of this looks right, and the other piece doesn't. Which piece looks right? The second one. What about the second one makes it look right when the first one doesn't look right? Yeah. So it's the location of your limits of integration. Right? Again, the second fundamental theorem of calculus says that the constant needs to be on bottom and the variable needs to be on top. And that actually happens on our second piece. I know it's not exactly just x up there. That's not a problem. We'll fix that. But the variable component is in the upper limit. So we had yet another theorem last time that said what to do that allowed us to switch limits of integration. So what did we have to do if we simply switched the limits of integration? How did that change the value? It changes the sign, exactly. So instead of having this, we will have this. Okay, that's how the first piece changes. So what about the second piece? Well, the second piece is already in the right sort of format. And on the first piece, now that we've switched the order of integration, the first piece actually looks the most like the fundamental theorem of calculus now, right? Second fundamental theorem. It does, because it actually has a number on bottom and plain old x on top. And so when we're taking the derivative of the antiderivative, so far all we've done is we've rewritten the right-hand side, right? This is still f of x. But I'm ready to take my derivative. And when I take my derivative now, I'm actually going to use that fundamental theorem. So this negative, it stays. And then according to the fundamental theorem of calculus, it says that I can do just x squared plus 4. And the reason, again, that that would work also is if you think about it, what's the derivative of x? Just 1. So if it helps you to remember every time to do it, just put the derivative of the upper limit of integration at the back anyway. If it's x, it'll be 1. You don't have to do anything different. On the second one, we're going to do the same thing. We're going to plug in the variable component. In this case, that would be 3 minus x squared plus 4. It's just 4. And then all of this needs to be multiplied by the derivative of the upper limit of integration. So what is the derivative of 3 minus x? Negative 1 on this one. So whatever it is with the value plugged in, it gets multiplied by the derivative of the upper limit of integration. And we're going to simplify, and your calculator can't help you with that. So let's just get it going. I have negative x squared minus 4. And then we have, these will be, well, let me do the negative in a minute. We have 9 minus 6x plus x squared plus 4. And we'll distribute through a negative. So I have negative x squared minus 4. 9 and 4 make 13 on the inside, so I have minus 13 plus 6x and minus x squared. So I have negative 2x squareds plus 6x minus 17. All good? Awesome. So from a visual perspective, we've kind of already talked about this, but you can ask the question much like the picture sort of looked when we did our calculators a moment ago. So on this problem, it's not giving you the setup, it's just giving you a verbal description of what it looks like. It says it's the area of the region bounded by y equals x squared, x equals 2, and the x-axis. So in order to do this problem, you're going to have to actually create this picture and then figure out what your function is and what your limits of integration are, and then do the calculus for the problem. This is a very familiar graph to you, though, right? I sure hope so. If you were sketching this graph, you'd get something like this. Agree? Okay. So the graph itself, I'm going to use, actually let me use a blue. So this is the y equal x squared. I need the line at x equal to 2. Is x equal to 2 a vertical line or a horizontal line? Vertical. So here's my line at x equal to 2. And then it says the x-axis, so I'm going to highlight the x-axis as well in blue. And what it needs is it needs the trapped area. And my graph isn't perfect, but do you see where the trapped area is? It's right in here, right? So we're going to create the antiderivative definite integral notation that we've been working with. The equation that I'm underneath is the equation x squared, and I'm going to do this with respect to x. What are my limits of integration? What was it, Emma?
Well, the bottom one's 0.
It is. What's the top one?
2.
It's 2. It's always values of x. So I need to figure out where did I start? Right here. This is x equals 0. And where do I end? This is x equal to 2. Okay? So then we're going to actually do the calculus part of this. So what's the antiderivative of x squared? Okay, so yeah, not plus c for the moment, right? Don't forget it for later, but 1/3 x cubed or x cubed over 3. We're going to evaluate it 2 and 0. A lot of times when we evaluate it 0, it becomes 0, not all the time. So be careful about that. But this would be 1/3 times 2 cubed minus 1/3 times 0 cubed. So again, I'm showing the very bare minimum of what you have to show. I mean, everything that's on this problem is exactly what I expect to see. What would I get for my final answer? 8/3 is correct. This is 8. All right, one more thing in this section. It's called the average value for integrals. So if we have a function that's integrable, that means you can take the integral of it, right? You can take the antiderivative on the interval AB, then the average value is the antiderivative times 1/b minus a. So I want to talk about what this equation is actually doing because it makes a lot of sense visually. So if you had a function, we know that this piece finds what? One word. What does it find? Area. It finds the area between A and B. Agreed? What this does is it averages things. So when you want to figure out in this class how what your grade is, and if you were keeping track points wise, you would actually divide by the total number of points in the class, right? That's what this is doing. This is dividing by the length of the interval. So if you think visually, here's A and here's B, then B minus A is this distance. It's taking the area and it's dividing by the width of the area. So it's giving you an average height. So visually speaking, let's say this were your curve and your area is in here. If you could take this area like you take Play-Doh or clay, and you could reformat it or reshape it, what this is doing is it's taking the area and turning it into a rectangle. It's averaging out the height. And it's actually kind of cool because graphically you can check this really well to see if you got the right answer at the end. So we're going to do a problem, we're going to check it at the end and you'll see what I mean. Okay, but that's what it's doing. It's giving you an average height over your width that you've chosen for your area. All right, so we're going to do one with a radical because we haven't done one yet with a radical. So it's asking me to find the average value. According to the formula in the previous slide, I have the integral over my interval 4 to 9 of my function dx. Please remember your dx's. I know you don't feel like they're that valuable or important now, but they're there for the purpose of those who are going to need them later on when you work with more than one variable. So just everybody remember, okay? Oh, I messed up. Didn't mean to put that there. And then on the front, I'm supposed to do 1 over b minus a. So that's 9 minus 4 in this problem, 1/5. So my width of my rectangle is 5 because it's going from 4 to 9. So I'm going to divide by 5 or multiply by 1/5. All right, so we recognize, of course, that I can rewrite this piece as what? Yeah, x to the 1/2. So instead, if you want to think about this, I'm doing from 4 to 9 of x to the 1/2 dx. All right, so what's the antiderivative of x to the 1/2?
2 over 3, x and 3 over 2. X
Okay.
raised to 3.
You're right. I'm going to write it differently just to make sure everybody sees where your pieces came from. So add 1 to my power, that's x to the 3/2. If I divide by the new power, 3/2, I'll have it. Dividing by fractions is really kind of ugly looking. So instead of dividing by that fraction, you could multiply by the reciprocal. So that's actually the 2/3 that she mentioned. next to the 3/2. In terms of evaluation, having 3/2 is also not super friendly looking. So this is, I'm gonna write 2/15. This is the square root of x cubed. And we're going to evaluate 9 to 4. So I have 2/15, the square root of 9 cubed. You can put the cubed on the outside or on the inside, it doesn't matter. And then 2/15, square root of 4 cubed. Because it's the square root of 9 and the square root of 4, you will get whole number values out of this one, just because it's those particular values. If it were different square roots, you would not necessarily. But if you evaluate this, you will end up getting in fractional, or fractional forms, what I have written down, 38/15. Okay, so I'd like you to grab your calculator. Last thing to do for this today. I would like you to put the original equation in the calculator. Okay, the integral, not the integral, I'm sorry, the function square root of x, just y1 equals square root of x. And I'd like for you to take your interval, and I'd really like for you to do it from 4 to 9. So how you do that, if you'll remember, is that you do window, you do x minimum 4, x maximum 9, and for the purposes of what we're doing, negative 10 to 10 is still fine on your x or your y values. It won't hurt anything. It's going to look a little squished, but it's okay. And then in y2, I want you to put 38/15. And then graph. Because it's squished, my window's not great. I'm going to make it go from 0 to 10 on the y-axis. I think that'll be better. So what you should be getting, if it's a squished view like mine anyway, is it looks like this. It's very, very shallowly sloped. It's not very strong. In fact, I know what the graph's supposed to look like, so it has to be more like, we're only looking from 4 to 9. So it looks like that. And then this line at 38/15 looks like it's cutting right through. Do you see that? And so what you should be convinced of when you're looking is that there's approximately a balance. You can't verify it visually, but it should look reasonable visually. If it doesn't look reasonable visually, there's a problem, either in your calculus on the original work or maybe in something how you put it into the calculator. But it gives you kind of a red flag of, I need to go back and figure out where my error is. So that's a very helpful step on that particular problem. Notice we didn't find any areas on my screen. I'm just verifying that it averages out the height visually speaking. Okay?